The next speaker of this session is Charis Anastopoulos, and he's a professor at University of Patras, and he's going to talk about quantum field theory-based quantum information, measurements, and correlations. So Charis, you have 25 minutes for your talk. 5 minutes before the end, I'm going to give you a warning. And after the talk, everyone has 5 minutes to ask you questions. Whenever you're ready, the floor is yours.
Yes. All right. So I'm going to talk about a program that we have been developing in the last years about measurements in quantum field theory and their applications to quantum information, among other things. The main work in this program is with my collaborator, Dina Savidou, and also recently we have been working with Veilok Hu on the aspects that have to do with measurement, with the information and applications to non-equilibrium QFT. So what is the point of the program? So the idea is that, of course, we want to do relativistic quantum information, and there appears to be a convergence on the topics, but what is missing is that we are using information as it has been developed in the context of non-relativistic quantum mechanics. What we would like in a relativistic quantum information is the first principle analysis in the context of quantum field theory. So this is why the title of the talk is QFT-based quantum information. We want to base quantum information from first principles in QFT. Now, certainly QFT, because there is no consistent relativistic quantum physics without QFT. And we want a theory that will share the properties of relativistic QFT. We need to have covariance, and we need to have locality, and we need to have causality. So all the important properties of QFT must be present in the quantum information theory that will be developed. So our point is that to do that, we need a theory of quantum QFT measurements. And this theory of QFT measurements must be consistent, physically consistent in itself. It's a very big challenge, but it also has to be practical. We need to be able to use it to get predictions on on current experiments. So where is the problem? Now, let's see first. There are some problems in order to formulate quantum measurements in QFT that come from the very foundations of relativistic quantum theory. The first problem has to do with the notion of causality, essentially. Suppose we do two measurements at space-like separated regions, and in a space-like separated regions, we can always choose a frame where measurement P will be before measurement Q, and another frame where measurement Q will be before measurement P. So if we take the standard axioms of projective measurement, in one frame you will have this sequence of states, but in the other frame we will have this sequence of states. First Q prime and then P prime. Where is the problem here? Because there is a space-time region where we have this parallelogram, where we have incompatible assignment of probabilities. So incompatible assignment of states, sorry. Probabilities are okay. There is no problem with probabilities. Because if we have space-time separated regions, we expect that the P and Q commutes in all reference frame, so probabilities are the same. So this result, this challenge, let's say, is known ever since at least the 60s, probably even earlier. And the standard resolution is that, as stated by Wigner, is that the quantum state cannot be taken as an objective. What matters is only probabilities for multiple measurements. So, okay, but if you want to do quantum information, you define informational quantities in terms of the quantum state. So if the quantum state is not an objective criterion, then you need some other way of formulating information in a relativistic system. So this is the first challenge, and the solution in the line of Wigner is, well, we have to work with probabilities about all possible sequences of measurements. This is covariant, this is invariant, this is a quantity that makes sense to base our information theory. Now, the second challenge is another foundational problem on quantum field theory is how do we define localization? So there are many theorems that localization cannot be sharply well defined in relativistic systems. Especially we have the theories by Malamud and the theories by Hegerfeld. Sharp localization is not compatible with relativistic causality, meaning a representation of the Poincare group with positive energy. And we have some theorems from Hegerfeld, again, positive energy is incompatible even with unsharp localization. In both cases, we have signals faster than light if we assume localization exists. Of course, we assume causality, so there is a problem with how you formalize localization. The third challenge is, well, has been well discussed in this conference, is Sorkin's, let's say, paradox that, which in effect, it means, among other things, that we should not use ideal measurements in QFT because they might lead to contradiction with causality. Now, this is because the standard state update rules, the state reduction rules, essentially implies that when we reduce the quantum state, the reduction takes place over the whole Cauchy surface instantaneously, and it's only to be expected that this would lead to problem with causality. Now, this does not mean that we cannot use quantum measurement theory, just that we cannot use ideal measurement. And why is this important? In the context of information, everything we do in quantum information presupposes that we have access to ideal measurements, because you have minimization over all possible measurements, for example, and when you do that, you have the extreme elements which correspond to ideal measurements. So if we do not have ideal measurements, we need to define differently informational quantities. Now, these are challenges to overcome, and these challenges were partly known quite a long time now. If you see the axiomatic formulations of quantum theory, standard quantum theory, all axiomatic formulations have one axiom that involves quantum state reduction, how you update the quantum state after measurement, or if you want, how do you define conditional probabilities, or how you define joint probabilities, depending on the axiomatization. However, if you look at the axiomatic frameworks for QFT, Whiteman axioms, Kastler axioms, they do not include state update actions. Why is this? Because the emphasis in QFT is on scattering, because most applications have been historically on high energy physics. High energy physics is concerned with scattering, and we are more interested in asymptotic states and to have properties like asymptotic completeness rather than real-time evolution. And of course, most of the research in high energy physics, the overwhelming majority, just uses S matrix. Cross sections, particle masses, decay rates, they are all determined by the S matrix. But there are at least two regimes where S matrix is not enough. One this regime is in quantum optics. When you have multi-time correlation experiments like in bunching and anti-bunching phenomena, if you are rigorous conceptually about it, this type of correlations involve joint probabilities, and as joint probabilities, you have to use the state update rule in order to define. No matter how you compute these quantities in practice, at the fundamental level, you need to have the state update rule. And if you have this type of experiments in cutting-edge experiments, like, for example, experiments in space, you are going to need to be more rigorous in determining this probability. And there are many cases in cosmology, condensed matter physics, non-equilibrium QFT, where you have real-time evolution and not only asymptotic. So one of the good things on the formalism we're going to present is that it connects between measurements and real-time evolution, which is, we will see how it goes. So the main interaction is we need to formulate in quantum measurement theory. To this end, we need to formulate the interaction between a measurement apparatus and the quantum field that is being measured. And of course, this has to be done only in terms of quantum fields. So you need essentially a QFT interaction between detector and field. Now, some very brief summary of the history of measurement. Well, you have seen already quite a bit today. So I'm just going to say that Landau and Pearl were the first to discuss measurability of quantum fields, and Bohr and Roosevelt corrected them in their classic paper in the 30s. The most successful QFT measurement theory, which is the prototype for any other measurement in terms of its success, is Glauber photon detection theory. It is a QFT measurement theory. In effect, it has a large amount of applications in quantum optics. Of course, it's problematic. It works only for photons. It has a splitting into positive and negative frequencies in the probability assignment, which is not a local operation, but it's successful. It predicts experimentally well, it's useful. So in this sense, this is our prototype. Now, you saw about Unruh-Dewitt detectors. There's quite a bit of discussion. The Unruh-Dewitt detector is essentially a point-like system acting as a detector. So this is not, strictly speaking, a QFT. So in principle, you might have problems with causality, and you need a fundamental justification. And you have also seen today, again, by Chris Fuster, for example, how you can formulate in a QFT measurements in order to solve problems like Sorkin's causality problem. And our approach, we call it the quantum temporal probabilities, because the aim was initially to construct probabilities for temporal quantities. So these temporal quantities, as it turns out, are essential for measurements in QFT. I'm going to explain about that. First, let me say what is our aim. We have three distinct aims. The first aim is the foundational, it's medium term. We want to see how shall we complete QFT by adding an action for state update. So eventually we want a new axiomatization. Second is pragmatic. There are experiments, especially in space, that need non-trivial, that are non-trivial, and they need first principle predictions for photo detection, for example. And third, what I'm going to talk about here is quantum information. We want to define relativistic quantum information from first principles, QFT, in terms of probabilities for measurement outcome. So what are the physical ideas of the QTP approach? First, how we model measurement. We have an interaction between a quantum system and the measurement apparatus. The quantum system, the measurement apparatus must be macroscopic. What is macroscopic in quantum theory? There is a good formulation in terms of the coherence condition in the coherent histories approach. This means that the pointer variable is highly coarse-grained. Pointer variable is what points at the result of the measurement, and that we're talking about histories of these measurement outcomes, and this must satisfy the coherence condition. If we don't have a macroscopic detector, this is not really a measure. The second assumption is, what do we actually measure? So if we go to a particle accelerator and we see what are we doing when we are measuring particles, all particle events are localized in time. Any event of measurement has a specific location, a specific detector in a specific elementary detector that detects it, which means it is a location in space, and it is detected at a particular time. The time is determined, for example, by the connection with a with a computer when we have a current. So position and time are measured quantities for any detection events. So the space-time location of an event. It's not short, of course, but they are random variables in any experiment. So the very minimum that we need from a measurement theory is that it should determine probabilities density for multiple detection events. Definitely space-time point of the event, of the detection event, plus any other quantities. Quantities like momentum, energy, spin, and so on. And the third is QFT measurements require observables that are intrinsically temporal. This is a challenging problem with a long history of how to define temporal observables in quantum theory. And the key point is that time is a parameter. It's a random variable in the system when it's not predetermined, like, for example, in some measurement theories of von Neumann, which predetermine the time of measurement. Time is genuinely not predetermined. So we're based on consistent histories. I'm not going to say much about the coherent histories. I'm just making this statement. We use many ideas and tools from the coherent histories program, developed by Griffiths, Somnay, Gell-Mann, and Hartley in the 80s and 90s, especially in relation to the classicality of the detector. So the idea is that the fundamental object is not the state, but the history, and that a history is a sequence of measurements, or the coherent history of properties of the system, and we can determine probabilities for this measurement if the coherence condition is satisfied. So the coherence condition is essentially for the proper definition of probabilities, and we need to assume that it holds for the detector outcomes. I'm not going to say anything else. I'm just going to say that there is a very precise meaning in the word the coherence condition and quasi-classicality we need in order to define probabilities. So how does this work? We have a coupling between a field and the apparatus, field Hilbert space, apparatus Hilbert space. So we have a local composite operator for the field, which can be the field operator itself. It can be the electric current, the weak current, electromagnetic field tensor, depending on what we want to measure. And J is a current operator in the Hilbert space of the detector of the apparatus. So this is the coupling. And to leading order in perturbation theory, it's very easy. I'm going to show you an elementary derivation, not the technical one based on QTP and the coherent histories. So to leading order in perturbation theory for the coupling, it's easy to determine that the probability density after the convolution is of this form. Here you have the 2-point function for the composite operator of the coupling. This, as I said, this can be the field, this can be the electric current, and any other composite operator. And this is the detector kernel. It contains information about the detector. You see, J is the current of the detector. Pi is a measurement of the pointer variable in the detector. P here is the space, is the energy momentum vector for the detector, and so on. So the probability is a linear functional of a 2-point correlation function. So how to do this? You can just take very elementary calculation, just half a page calculation. You just assume the coupling with the switching function. The switching function, well, physical couplings in QFT do not have switching functions. So the switching function essentially mimics sampling of position. And we calculate the probability to lowest order in perturbation theory. And from that, we can define a probability measure modulo sum the convolution with respect to F. So this is a very, very simple proof. The proof using QTP starts from constructing the histories. So it's conceptually more rigorous, but it agrees at the level of perturbation, at lowest order perturbation theory. So we can use this perturbation theory derivation. And this works for N detectors. For N detectors, you see we have the 2N time correlation function. We have time ordered for N composite operator, anti-time order for N, and then you have N copies of the detector kernel for the N different measurements. So again, this is determined to lowest order in perturbation theory. The calculation is very simple. And we can write that in an index notation that is very helpful. The arguments, Greek letters for the arguments of the correlation function, and Z arguments for the measured observables. Now, the key point I want to show is that this correlation function has N time order elements and N anti-time order elements. It's not the usual correlation function that we learn in QFT, for example, in the S matrix, which has only time order. It's different. It's a very different object. It has quite different properties. And this type of correlation functions appear in the CTP formalism or the Schwinger-Keldysh closed time path formalism. This is a formalism that solves the other problem that S matrix cannot solve the dimension, real time causal evolution. So it was originally developed by Schwinger and Keldysh, but it has found many applications, especially in non-equilibrium QFT, condensed matter and cosmology. And the idea is that it describes real-time evolution in terms of correlation functions, which are mixed, have n time order components and m anti-time order components. And this is a generating functional, it has a path integral expression, and we can write everything in terms of path integral. Now, getting a connection of our measurement theory with CTP is very, very nice, and we have this connection for one reason. We can borrow the path integral from CTP. So we can have a measurement theory for quantum fields that uses path integral. Technically, this is a great, great help for many things. So now what happens here is that now there is a lot of discussion about CTP, a lot of work. What I'm just going to point out this crucial point. These correlation functions here have n time order and m anti-time order points. Now, in CTP, in QTP, in measurement, we have n equal m. So we need only the diagonal. We need the correlations that... 5 minutes. Okay, we need only the correlations that have the same number of time order and anti-time order. So if we take the diagonal part, let's say, of the generating functional, we can straightforwardly relate it to the generating functional of measurements, of probabilities for measurements. And we get a very simple expression that relates the probabilities of measurements in our model in QTP with the generating function for CTP. So CTP describes real-time evolution, QTP describes joint probabilities, and this formula joins them. And the good thing is that we can write path integrals, we can express probabilities for measurements in terms of path integrals. So this is a list of applications. We have mainly worked on this topic. So since I have 5 minutes, I'm going to go straight away to the main result, to 2 of the results. One result is that we can prove Glauber's theory is obtained as a limit when we assume the so-called rotating wave approximation. In fact, we don't need to assume it. In many, many setups, the rotational wave approximation holds by default. It's a good approximation. It's not an additional assumption, but we have to assume that the kernel, the detector kernel, which we mentioned, is proportional to a delta function. Essentially, that the characteristic scales of the detector are much smaller than any parameters that characterize the initial state of the field. So we get Glauber's theory as a limit. The situation is a bit more complex. So in some cases, we get different predictions from Glauber's theory. And this is important to explore in relation to experiments in space. And we also get partly unroot-David detectors as a limit. How do we, from the QTP probability formula, first we shrink the detector's world cube to a single trajectory. Remember, we have space-time sapling, and we just take the space-time sapling to be a single trajectory. And then we have to assume that the current operators for the detector evolve in terms of a Hamiltonian. This way, this is the crucial assumption. Now, this assumption holds when we have paths in the inertial frame, so inertial paths, essentially inertial trajectories. In general, it's not true for non-inertial trajectories if we're trying to be rigorous, but, and here is the challenge and the interesting thing, it might be justified if we have a non-well-defined Hamiltonian, meaning it's singular, and at the same time regularize the Hamiltonian to make it regular, and then take the limit of shrinking the world cube. So this is the possible way that we can justify unroot-David detectors outside inertial trajectories. So this is for the future. And I think I'm going to stop here, and I'm going to say a rigorous extension of quantum information to QFT requires a consistent and practicable theory of QFT measurement. This is our message, let's say. Now, our approach aims to provide this theory, and it's a good thing that it converges with the CTP formalism, and this broadens the scope of our applications. And the main message, take-home message, I might say, is that QFT information should be contained in the unequal time correlation functions. These appear naturally in the probability assignment, but these are not defined at a single moment of time. So information measures should not be defined with respect to the single time quantum state, which, as we saw, has many conceptual problems. So this is work in progress. Thank you.
Thank you, Charis, for the great talk.